with deterministic computation, the next state is certain. Under non-deterministic computation, the next state is not certain. Okay, so the essence, right? Okay, so we've said all that. So under non-deterministic, there is more than one possible next state. Okay. Now, I'll make a few more comments. Non-determinism is a sort of, you're generalizing the notion of determinism. So, you know, if the next state comes out with a certain probability, well, it's possible that probability might be 100%. Okay? So in other words, determinism is a sort of subset, it's a subcategory. It's subsumed by a more general concept of non-determinism. Like you could say, deterministic computing is a special case of non-deterministic computing. It's a special case when the probability of a given state being the next state is 100%, whereas for non-deterministic computing it's not 100%. Right? So in that sense, determinism is a subset, like it's a special case of non-deterministic computing. Right? Now we can draw finite automata that are deterministic. We've been doing that. You know how to do that now. But we can also draw finite automata that are non-deterministic, and they have certain features, certain properties that are a bit different from your deterministic finite automata. Now, we're going to use these terms deterministic finite automata a lot, and non-deterministic finite automata a lot. So we will just abbreviate them. So we'll see fairly common abbreviations, like here, deterministic finite automaton. It just gets abbreviated to DFA. Okay, so remember that, because we will use this a lot in the future. So DFA. Okay, and a non-deterministic finite automaton gets abbreviated to NFA. Right? Things are getting a little dark again. What's the time? It's only a bit after 4 p.m. Where is my hat? Where is my hat? Just a minute, I'll put on my hat. And turn on the light, a bit more light. Okay, so, alright, so DFA, deterministic finite automaton, and a non-deterministic finite automaton, and an NFA. Okay, so remember those two abbreviations. Now here you have our first example of a state diagram, state transition diagram, of our first non-deterministic finite automaton, an NFA. So just labeled N, short for non-deterministic. And our first example, so 1, so N1. Okay? And here is our first example of an NFA. Okay? Now have a look at it. Do you notice some differences from what you're used to with DFAs? Okay? We've been dealing with DFAs up to this point, and now here's our first NFA. Do you notice some differences? Let me just have a look. I won't spend too much time, but I'll give you some clues. You spot, and you play the game. Spot the differences. Well, I'll give you some clues. Have a look at this. Here's one difference. Here's another one. Okay. Right. So now, why did I say that? Well, look, we have here. We're in a given state, say Q1, and an input symbol comes in. Let's say it's a 1. Let's say the alphabet is just a binary alphabet, 0 and 1. So we're in a given state, the input signal 1 comes in, and we transition to Q1 and to Q2. Ooh, that's different, right? Like I say, more than one possible next state. Well, the next state might be Q1 or might be Q2, right? So that's non-deterministic. And this eta here, what's that? What's that all about? Why is that there? Because in a DFA, a deterministic finite automaton, these labels here on the transitions, they are symbols of your alphabet. Right? They have to be symbols of your alphabet. But the eta, that's not a symbol of your alphabet, right? Eta means the empty string, right? No symbol. So but we've got an eta here. So what's all that about? So that's odd. So there's like two differences at least. Okay. So just by inspection, you can see there are some essential differences between a DFA and an NFA. Right? So I'll start listing some, and I'll explain what this eta and so forth. Probably more on the next session. But let's start talking about the differences now between a DFA and an NFA. Right? Now, with the DFA, for each state, okay, for every state, and for each symbol in your alphabet, there will be only one and only one, exactly one, exiting arrow from that state. Okay? And that's the case with the DFA. Right? I can say it again a different way. There's only one next state in a DFA when you're in a given current state, and a given input symbol comes in, and therefore there's only one next state. In other words, there's only one exiting arrow for that pair. The pair being the given current state and the given input symbol. Okay, there's only one for that pair. There's only one exiting arrow to some other next state. Only one, exactly one and only one. Okay. Right. Now with an NFA, a non-deterministic finite automaton, it breaks that rule. Right? Because here's an example. You're in a given state, input symbol 1 comes in, and it goes to two different states. It could go to Q1 or it could go to Q2. Okay? So, state here, Q1 has one exiting arrow for 0. That's okay. That would be like a DFA. But it has two exiting arrows for symbol 1. Right? There's one exiting arrow and there's another one. Okay? Now, state Q2, it has one arrow for 0. That's sort of that would be normal for a DFA, and none for 1. There's no mention here. There's no arrow for 1. Now with the DFA, you have to have an exiting arrow for every pair of current state and current input symbol. Okay? But here, there's a missing arrow for the symbol 1, the input symbol 1. Right? So there's something odd here. No arrow labelled 1. Alright, well, continuing on would be in the next session, so I'll stop here and just go straight on in the next session.